In this lesson, we're going to define what we mean by extrema for a function on an interval. So let's start by considering the graph of this function, f of x equals x squared plus 1, for x greater than or equal to -1 and less than or equal to 2. So x is in the interval from -1 to 2 with closed brackets. Remember, the closed brackets means that x can actually take on the value of -1 and -2. Now here we have the graph of this function down here, and you'll notice that at this point right here, that's the maximum value for the function for all x between -1 and 2. So notice that f of 2, that's equal to 2 squared plus 1, and that's 5. And you'll notice that f of x, for all the other x values in this interval here, f of x is less than or equal to 5, and that's for x, all of the other x values in that interval. So we call this number 5 right here a maximum or absolute maximum for our function f of x over this interval. Now it's also important to note that f of x actually attains its maximum value, meaning that there is a number in this interval. In this case it's the number 2, where f of 2 is actually equal to 5, which is the maximum. So we say f of x attains its maximum value. Now you'll also notice that we have a minimum value right here. So you notice that f of 0 is equal to 1. Right, there's 0 on the x-axis, and f of 0 is equal to 1, and you'll notice that f of x is greater than or equal to 1 for all the other x values in this interval. Just by looking at the graph, you can see that. So we call this number 1 a minimum or absolute minimum for f of x over this interval. Now it's also important to note that f of x actually attains its minimum value. So there is a number in this interval in which f of that number is equal to 1, that number being 0 in this particular example. So we have the following definition then based on this example. So here's our definition for extrema. If we let f of x be defined on some interval I containing the number c, then f of c is called the minimum or absolute minimum of f over the interval I, provided that f of x is bigger than or equal to f of c for all x in the interval I. On the other hand, f of c is called the maximum or absolute maximum of f on I, provided that f of x is less than or equal to f of c for all x in I. Now in the previous example, for the minimum, the c was equal to 0, and you notice that f of c, or f of 0, was 1, and that was our absolute minimum. And for the maximum, the c was equal to 2, and f of c, or f of 2 in that case, was 5, and that was our absolute maximum. Now let's consider this example. So it's the same function as before, f of x equals x squared plus 1, but now x is going to be between -1 and 2, but it doesn't actually take on the value of the endpoints -1, nor does it take on 2. So x is only taken between 1 and 2, and we have open parentheses around the -1 and 2, defining the interval over which x varies. Now here we have the graph of what this function would look like. Notice we have open circles here because x never actually reaches the value of 2, and we have an open circle over here at the other endpoint because x never actually takes on the value of -1. Now you notice for this function, the maximum value is still 5, right? The maximum value still has to be 5. However, f of x never actually attains its maximum value of 5. In other words, there is no value c in here where f of c ever equals 5. C would have to be 2, but 2 is not in this set. So f of x never actually attains its maximum value. It gets infinitely close to it, but it never actually attains it. Notice as x approaches 2 from the left, f of x does approach 5, but it never actually reaches it. Now, this example and the previous example illustrate the extreme value theorem. Now here's the extreme value theorem, and it makes this statement. If f of x is continuous on a closed interval, the word closed is very important here, then f of x attains both a minimum and a maximum value on the interval. Now if you think back to the previous two examples, for the first example we had f of x being defined as this function over the interval from -1 to 2, closed brackets, and we saw that f of x actually did attain its maximum value and it attained its minimum value. But for the next example then, we saw that for the same function defined over an open interval, we saw that f of x did not attain its maximum value of 5. If you look back at the graph, it did actually still attain its minimum value. F of 0 is 1 and 0 is in this interval, but it did not attain its maximum value. And so that's why for the extreme value theorem we require that the function be defined on a closed interval. And it also has to be continuous for this result to hold, for f to actually attain its minimum and maximum values. All right, so that illustrates the extreme value theorem, as well as the concept of what an extrema is for a function over an interval.